Hey guys, how's going on? Hmm. Okay, let me continue with the book on page 77. But what happens if a function must return some other type? Okay, here on many numerical functions like squared, sin, and cos return double. Other specialized functions return other types. To illustrate how to deal with this, let us write and use the function a to f, which converts the string s to its double precision floating point equivalent. A to f is an extension of a to I, which we wrote versions of in chapter 2, which we wrote versions of in chapters 2 and 3. In handless and optional sign and decimal point, hang on. And the presence or absence of either integer part or fractional part. This is not a high-quality input conversion routine. That would take more space than we care to use. First, A to F itself must declare the type of value it returns. Since it is not int because float is converted to double in expressions. Hang on. The type named precedes the function name like this. Like these words. Second, and just as important, the calling routine must state that A to F returns a non-int value. The declaration is shown in the following primitive desk calculator. Barely adequate for checkbook balancing, which reads one number per line, optionally preceded by a sign, and adds them all up, printing the sum after each input. I'm sorry. Okay, fine. Let me focus on this. The declaration double sum, comma A to F parenthesis semicolon says that sum is a double variable and that A to F is a function that returns a double value. Is a mnemonic. It suggests that sum and A to F are both double precision floating point values. And as A to F is explicitly declared in both places. See, assuming instead it returns an integer, and you'll get nonsense answers. If A to F itself and the call to it in main are typed inconsistently in the same source file, it will be detected by the compiler. But if as is more likely A to F were compiled separately, the mismatch would not be detected. A to F would return a double, which main would treat as an int, and meaningless answers would result. Lint catches this error. Given A to F, we could in principle write A to I, convert a string to int in terms of it. Notice the structure of the declarations and the return statement. The value of the expression in return is always converted to the type of the function before the return is taken. Therefore, the value of A to F, a double, is converted automatically in int when it appears in a return. Since the function A to I returns an int, the conversion of a floating point value to int truncates any fractional part. As discussed in Chapter 2, Exercise 4 Middle School 2 extend A to F so it handles scientific notation of the form like this, where a floating point number may be followed by e, lowercase e or uppercase e, and an optionally signed exponent. 4.3 More amplification arguments. Hang on. In Chapter 1, we discussed the fact that function arguments are passed by value. That is, the called function receives a private temporary copy of each argument, not its address. This means that the function cannot affect the original argument in the calling function. Within a function, each argument is in fact a local variable initialized to the value with which the function was called. When an array name appears as an argument to a function, the location of the beginning of the array is passed. Elements are not copied. The function can alter elements of the array by subscripting from this location. The effect is that arrays are passed by reference. In Chapter 5, we will discuss the use of pointers to permit functions to affect non-arrays in calling functions. By the way, there is no entirely satisfactory way to write a portable function that accepts a variable number of arguments, because there is no portable way for the called function to determining how many arguments were actually passed to it in a given call. Thus, you can't write a truly portable function that will compute the maximum of an arbitrary number of arguments, as we use the max built-in functions of Fortran and PL/I. It is generally safe to deal with a variable number of arguments if the called function doesn't use an argument which was not actually supplied, and if the types are consistent. Printf, the most common C function with a variable number of arguments, uses information from the first argument to determine how many other arguments are present and what their types are. It fails badly if the caller does not supply enough arguments, or if the types are not what the first argument says. It is also non-portable and must be modified for different environments. Alternatively, if the arguments are of known types, it is possible to mark the end of the argument list in some agreed upon way, such as a special argument value, often 0, that stands for the end of the arguments. 4.4 External variables. A C program consists of a set of external objects, which are either variables or functions. The adjective external is used primarily in contrast to internal, which describes the arguments and automatic variables defined inside functions. External variables are defined outside any function and are thus partitionally available to many functions. Functions themselves are always external because C does not allow functions to be defined inside other functions. By default, external variables are also global so that all references to such a variable by the same name, even from functions compiled separately, are references to the same thing. In this sense, external variables are analogous to Fortran common or PS-external. We will see later how to define external variables in functions that are not globally available, but are instead feasible only within a single source file. Because external variables are globally accessible, they provide an alternative to function arguments and return values for communicating data between functions. Any function may access an external variable by referring to it by name. If the name has been declared somehow, if a large number of variables must be shared among functions, external variables are more convenient and efficient than long argument lists. As pointed out in Chapter 1, however, this reasoning should be applied with some caution, for it can have a bad effect on program structure and need to programs with many data connections between functions. A second reason for using external variable for using external variables concerns initialization. In particular, external arrays may be initialized, but automatic arrays may not. We will treat initialization near to the end of this chapter. The third reason for using external variables is their scope and lifetime. Automatic variables are internal to a function, but they come into existence when the routine is entered. And disappear. Hang on. And disappear when it is left. External variables, on the other hand, are permanent. They do not come and go, so they retain values from one function invocation to the next. And thus, if two functions must share some data, yet neither calls the other, it is often most convenient if the shared data is kept in external variables rather than passed in and out via arguments. And let us examine this issue further with a large example. The problem is to write another calculator program better than the previous one. This one permits plus, minus, multiply, division, and equal to print the answer. Because it is somewhat easier to implement, the calculator will use reverse Polish notation instead of infix. Reverse Polish is the schema. Reverse Polish is the scheme. Reverse Polish is the scheme used by, for example, Hewlett-Packard pocket calculators. In reverse Polish notation, each operator follows its operands and infix expression like this. Hang on. Okay, I'm sorry. Okay, here we go. Like this, it's entered as like this. Parentheses are not needed. The implementation is quite simple. Each operand is pushed onto a stack. When an operator arrives, the proper number of operands, 2 for binary operators, are popped. The operator applied to them and the result pushed back onto the stack. In the example above, for instance, 1 and 2 are pushed. They are replaced by their difference, -1. Next, 4 and 5 are pushed and then replaced by their sum, 9. The product of -1 and 9, which is -9, replaces them on this stack. The equal operator prints the top element without removing it, so intermediate steps in a calculation can be checked. The operations of pushing and popping a stack are trivial, but by the time error detection and recovery are added, they're long enough that it is better to push each in a separate function than to repeat the code throughout the whole program. And there should be a separate function for fetching the next input operator or operand. Thus, the structure of the program is like this. Okay, here. Program like this. The main design decision that has not yet been discussed in where the stack is, that is, what routines access it directly. One possibility is to keep it in main and pass the stack and the current stack position to the routines that push and pop it. But main doesn't need to know about the variables that control the stack. It should think only in terms of pushing and popping. So we have decided to make the stack and its associated information external variables accessible to the push and pop functions, but not to main. Translating this outline into code is easy enough. The main program is primarily a big switch on the type of operator or operand. This is perhaps a more typical use of switch than the one shown in chapter 3. Like this code. So long. A whole page. Okay. Like this until this. The command C clears the stack with the function clear, which is also used by push and pop in case of error. We will return to get top in a moment. As discussed in chapter 1, a variable is external if it is defined outside the body of any function. Thus, the stack and stack pointer, which must be shared by push, pop, and clear, are defined outside of these three functions. But main itself does not refer to the stack or stack pointer. The representation is carefully hidden. Thus, the code for the equal operator must use push, parentheses, pop, parentheses, and semicolon. To examine the top of the stack without disturbing it, Notice also that because plus and multiply are commutative operators, the order in which the popped operands are combined is irrelevant. But for the minus and divide operators, the left and right operands must be distinguished. Exercise 4 middle score 3. Given the basic framework, it is straightforward to extend the calculator. Add the modulus percent and unary minus operators. Add an erase command which erases the top entry on the stack. Add commands for handling variables. 26 single-letter variable names is easy. 4.5 Scope rules. The functions and external variables that make up a C program need not all be compiled at the same time. The source text of the program may be kept in several files, and previously compiled routines may be loaded from libraries. The two questions of interest are: how are declarations written so that variables are properly declared during compilation? How are declarations set up so that all the pieces will be properly connected when the program is loaded? The scope of a name is the part of the program over which the name is defined. For an automatic variable declared at the beginning of a function, the scope is the function in which the name is declared, and variables of the same name in different functions are unrelated. The same is true of the arguments of the function. The scope of an external variable lasts from the point at which it is declared in a source file to the end of that file. For example, if file sp, push, pop, and clear are defined in one file in the order shown above, that is, like this, then the variables va1 and sp may be used in push, pop, and clear simply by naming them. No further declarations are needed. On the other hand, if an external variable is to be referred to before it is defined, or if it is defined in a different source file from the one where it is being used, then an external declaration is mandatory. It is important to distinguish between the declaration of an external variable and its definition. A declaration announces the properties of a variable. A definition also causes storage to be allocated. If the lines like this appear outside of any function that define the external variables sp and val, cause storage to be allocated and also serve as the declaration for the rest of that source file. On the other hand, the lines declare for the rest of the source file that sp is an int and that va1 is a double array whose size is determined elsewhere, but they do not create the variables or allocate storage for them. There must be only one definition of an external variable among all the files that make up the source program. Other files may contain external declarations to access it. There may also be an external declaration in the file containing the definition. Any initialization of an external variable goes only with the definition. Array sizes must be specified. Array sizes must be specified with the definition, but are optional with an external declaration. Although it is not a likely organization for this program, va1 and sp could be defined and initialized in one file, and the functions push, pop, and clear defined in another. Then these definitions and declarations would be necessary to tie them together. Because the external declarations in file 2 lie ahead and outside the three functions, they apply to all. One set of declarations surfaces for all of file 2. They apply to all. One set of declarations surfaces one set of declarations surfaces for all of the one set of declarations surfaces for all of file 2. For larger programs, the hash include file inclusion facility discussed later in this chapter allows one to keep only a single copy of the external declarations for the program and have that inserted in each source file as it is being compiled. And hang on. Sorry. And okay. Sorry. Let us now turn to the implementation of getTop, the function that fetches the next operator or operand. The basic task is easy. Skip blanks, tabs, and new lines. If the next character is not a digit or a decimal point, return it. Otherwise, collect a string of digits that may include a decimal point and return number. The signal that a number has been collected. The routine is substantially complicated by an attempt to handle the situation properly when an input number is too long. getTop reads digits, perhaps with an intervening decimal point until it doesn't sing anymore, but only stores the ones that feed. If there was no overflow, it returns number and the string of digits. If the number was too long, however, getTop discards the rest of the input line so the user can simply retype the line from the point of error. It returns too big as the overflow signal. Hang on. Okay. Like these words so long. We are engaged and engaged. It is often the case that a program reading input cannot determine that is, it has read enough until it has read too much. One instance is collecting the characters that make up a number until the first non-digit is seen. The number is not complete. The number is not complete, but then the program has read one character too far, a character that it is not prepared for. The problem would be solved if it were possible to unread the unwanted character. Then, every time the program reads one character too many, it could push it back on the input. so the rest of the code could behave as if it had never been read. Unfortunately, it is easy to simulate in getting a character by writing a pair of cooperating functions. Get delivers the next input character to be considered, and get puts a character back on the input so that the next call to get will return it again. How, how they work together is simple. Engage puts the pushed back characters into a shared buffer, a character array. Get reads from the buffer. If there is anything there, it calls get char. It calls get char if the buffer is empty. There must also be an index variable which records the position of the current character in the buffer. Since the buffer and the index are shared by get and engage, and must retain their values between calls, they must be external to both routines. Thus we can write get and engage and their shared variables. It's like this. We have used an array for the pushback rather than a single character since the generality may come in handy later. Exercise 4 middle score 4. Write a routine and gets which will push back an entire string onto the input. Should NGS know about buff and buff BUFP, or should it just use engage? Exercise 4 middle score 5. Suppose that there will never be more than one character of pushback. Modify get and engage accordingly. Exercise 4 middle score 6. Our get and engage do not handle a pushback EOF in a portable way. Decide what their properties ought to be if an EOF is pushed back. Then implement your design. 4.6 Static variables. Static variables are a third class of storage in addition to the external and automatic that we have already made. Static variables may be either internal or external. Internal static variables are local to a particular function just as automatic variables are, but unlike automatics, they remain in existence rather than coming and going each time the function is activated. They remain in existence rather than coming and going each time the function is activated. This means that internal static variables provide private permanent storage in a function. Character strings that appear within a function, such as the arguments of printf, are internal static. An external static variable is known within the remainder of the source file in which it is declared, but not in any other file. External static thus provides a way to hide names like BUF and BUFP in the get and get combination, which must be external so they can be shared, yet which should not be visible to users of get and engage, so there is no possibility of conflict. If the two routines and the two variables are compiled in one file, as like this, then no other routine will be able to access BUF and BUFP. In fact, there will not conflict with the same names in other files of the same program. Static storage, whether internal or external, is specified by prefixing the normal declaration with the word static. The variable is external if it is defined outside of any function, and internal if defined inside a function. Normally, functions are external objects. Their names are known globally. It is possible, however, for a function to be declared static. This makes its name unknown outside of the file in which it is declared. In C, static connotes not only permanence but also a degree of what might be called privacy. Internal static objects are known only inside the function. External static objects, variables or functions are known only within the source file in which they appear, and their names do not interface with variables or functions of the same name in other files. External static variables and functions provide a way to conceal data objects and any internal routines that manipulate them so that other routines and data cannot conflict even inadvertently. For example, get and engage from a module for character input and pushback. BUF and BUFP should be static, so they are inaccessible from the outside. In the same way, push, pop, and clear form a module for stack manipulation. VAL and SP should also be external static. 4.7 Register variables. The fourth and final storage class is called register. Hang on. A register declaration advises the compiler that the variable in question will be heavily used. When possible, register variables are placed in machine register, which may result in smaller and faster programs. The register declaration looks like this, and so on. The end part may be emptied. Register can only be applied to automatic variables and to the formal parameters of a function. In this later case, the declaration looks like this. In practice, there are some restrictions on register variables reflecting the realities of underlying hardware. Only a few variables in each function may be kept in registers, and only certain types are allowed. The word register is ignored for excess or disallowed declarations, and it is not possible to take the address of a register variable, a topic to be covered in Chapter 5. The specific restrictions vary from machine to machine. As an example, on the PDP-11, only the first three register declarations in a function are effective, and the types must be in char or pointer. 4.8 Block structure. C is not a block structure language in the sense of PEL, Sunshine, or Argo, in that functions may not be defined within other functions. On the other hand, variables can be defined in a block structured fashion. Declarations of variables, including initializations, may follow the left brace that introduces any compound statement, not just the one that begins a function. Variables declared in this way supersede any identically named variables in outer blocks and remain in existence until the matching right brace. For example, in this, the scope of the variable I is the true branch of the if, and the I is unrelated to any other I in the program. Block structure also applies to external variables, given the declarations like this. Then within the function f, occurrences of x refer to the internal double variable. Outside of f, the refers the outside of f, they refer to the external integer. The same is true of the names of formal parameters. Within the function f, z refers to the formal parameter, not the external. 4.9 Initialization. Initialization has been mentioned in passing many times so far, but always peripherally, to some other topic. This section summarizes some of the rules. Note that we have discussed the various storage classes. In the absence of explicit initialization, external and static variables are guaranteed to be initialized to 0. Automatic and register variables have undefined values. Simple variables, not arrays or structures, may be initialized when they are declared, but by following the name with an equal sign of a constant expression. Like this, for external and static variables, the initialization is done once, conceptually at compile time. For arithmetic and register variables, it is done each time the function or block is entered. For arithmetic and register variables, the initializer is not restricted to being a constant. It may in fact be any valid expression involving previously defined values, even function calls. For example, the initializations of the binary search program in Chapter 3 could be written as, instead of, in effect, initializations of automatic variables are just shorthand for assignment statements, which form to prefer is largely a matter of taste. We have generally used explicit assignments because initializers in declarations are harder to see. Automatic arrays may not be initialized. External and static arrays may be initialized by following the declaration with a list of initializers enclosed in braces and separated by commas. For example, the character counting program of Chapter 1, which came written instead as like this. These initializations are actually unnecessary since all are 0, but it's good form to make them explicit anyway. If there are fewer initializers than the specified size, the others will be 0. It is an error to have too many initializers. Regrettably, there is no way to specify repetition of an initializer, nor to initialize an element in the middle of an array without supplying all the intervening values as well. Character arrays are a special case of initialization. A string may be used instead of the braces and commas notation. This is the shorthand for the longer but equivalent. When the size of an array of any type is emptied, the compiler will compute the length by counting the initializers. In this specific case, the size is 4. 3 characters plus the terminating \0. 4.10 Recursion. C functions may be used recursively, that is, a function may call itself either directly or indirectly. One traditional example involves printing a number as a character string. As we mentioned before, the digits are generated in the wrong order. Low-order digits are available before high-order digits, but they have to be printed the other way around. There are 2 solutions to this problem. One is to store the digits in an array as they are generated, then print them in the reverse order, as we did in Chapter 3 with I to A. The first version of printd follows this pattern. The alternative is a recursive solution in which each call of printd first causes itself to cope with any leading digits and then prints the trailing digit. When a function calls itself recursively, each invocation gets a fresh set of all the automatic variables, quite independent of the previous set. Thus, in printd 1, 2, 3, the first printd has into 1, 2, 3 equal 1, 2, 3. It passes 1, 2 to a second printd, then prints 3 when that one returns. In the same way, the second printd passes 1 to a third, which prints it, then prints 2. Recursion generally provides no saving in storage, since somewhere a stack of the values being processed has to be maintained, nor will it be faster, but recursive code is more compact and often much easier to write and understand. Recursion is especially convenient for recursively defined data structures like trees. We will see a nice example in Chapter 6. Exercise 4 Score 7. Adapt the ideas of printd to write a recursive version of I to A, that is, convert an integer into a string with a recursive routine. Exercise 4 Score 8. Write a recursive version of the function reverse, which reverses the string s. 4.11 The C preprocessor. C provides certain language extensions by the means of a simple macro preprocessor. The hash-defining capability which we have used is the most common of these extensions. Another is the ability to include the contents of other files during compilation. File inclusion. The facilitated handling collections of hash defines to facilitate handling collections of hash defines and declarations, among other things. C provides a file inclusion feature. Anytime that looks like hash include file name is replaced by the contents of the file name. The quotes are mandatory. Often a line or two of this form appears at the beginning of each source file. To include comma, common, hash-defined statements and external declarations for global variables. Hash includes may be nested. Hash include is a preferred Hash include is the preferred way to tie the declarations together for a large program. It guarantees that all the source file will be supplied with the same definitions and variable declarations, and thus eliminates a particular nasty kind of bug. Of course, with an included file exchange, all files that depend on it must be recompiled. Hang on. Okay. Macro substitution. The definition of the form like this calls for a macro substitution of the simplest kind, replacing a name by a string of characters. Names in hash-define have the same form as the identifiers. The replacement test is arbitrary. Normally, the replacement test is the rest of the line. A long definition may be continued by placing a backslash at the end of the line to be continued. The scope of a name defined with hash define is from its point of definition to the end of the source file. Names may be redefined, and the definition may use previous definitions. Substitutions do not take place within quoted strings. So, for example, if yes is a defined name, there would be no substitution in printf yes. Since the implementation of hash define is a macro prepass, not part of the compiler proper, there are very few grammatical restrictions on what can be defined. For example, Orgo fans can say, okay, hang on. Can say like this, and then write like this. It is also possible to define macros with arguments. So the replacement test depends on the way the macro is called. Here's an example. Define a macro called max like this. Now the line like this will be replaced by the line like this. This provides a maximum function that expands into inline code rather than a function call. So long as the arguments are treated consistently, this macro will serve for any data type. There's no need for different kinds of max for different data types, as there would be with functions. Of course, if you examine the expansion of max above, you will notice some pitfalls. The expressions are evaluated twice. This is bad if they involve side effects like function calls and increment operators. Some care has to be taken with parentheses to make sure the order of evaluation is preserved. When invoked as score, there are even some purely lexical problems. there can be no space between the macro name and the left parenthesis that introduces its argument list. Nonetheless, macros are quite valuable. One practical example is the standard ICE natural library to be described in Chapter 7, in which getChar and putChar are defined as macros. Obviously, putChar needs an argument, thus avoiding the overhead of a function called per character processed. Other capabilities of the macro processor are described in Appendix A. Exercise 4, middle school 9, define a macro swap, which interchanges its two int arguments. Block structure will help. Chapter 5, pointers and arrays. Okay, this is a pointer is a variable that contains the address of another variable. Pointers are very much used in C, partly because they are sometimes the only way to express a computation, and partly because they usually lead to more compact and efficient code that can be obtained in other ways. Pointers have been lumped with the goto statement as a marvelous way to create impossible to understand programs. This is certainly true when they are used carelessly, and it is easy to create pointers that point somewhere unexpected. With this coupling, however, pointers can also be used to achieve clarity and simplicity. Hang on. This is the aspect that we will try to illustrate. For 5.1 pointers and addresses, since a pointer contains the address of an object, it is possible to access the object indirectly through the pointer. Suppose that x is a variable. Say an int, and that px is a pointer, created in some as yet unspecified way. The unary operator ampersand gives the address of an object, so the statement px equal ampersand x assigns the address of x to the variable px. Px is now set to pointing to x. The ampersand operator can be applied only to variables in array elements. Constructs like ampersand parentheses x plus 1 and ampersand 3 are illegal. It is also illegal to take the address of a register variable. The unary operator. Why? It is also illegal to take the address of a register variable. Why? The unary operator asterisk treats its operand as the address of the ultimate target, and accesses that address to fetch the contents. Thus, if y is also an int, it assigns to y the contents of whatever px points to, so the sequence, like this, it assigns the same value to y as does, like this. It is also necessary to declare the variables that participate in all of this. And the declaration of x and y is what we've seen all along. The declaration of the pointer px is new. Okay. Here I need a break. See you everyone.